Welcome to the Nuclear Weapons 101 series, a compilation of short presentations on nuclear weapons-related topics. The goal of this series is to improve nuclear literacy across the Department of Defense and promote a greater awareness of the critical role U.S. nuclear weapons serve in supporting the safety and security of America and her allies. These presentations are produced by the Nuclear Science and Engineering Research Center, an office of the Defense Threat Reduction Agency located at West Point, New York. This presentation is entitled Fundamental Nuclear Physics. The purpose of this briefing is to describe the basic physics that underpin nuclear weapon effects and functionality. An understanding of these principles, as well as their associated terms and units of measure, will better prepare viewers for future presentations on more technical topics, such as radiation detection and survivability. To begin with, all matter is made up of atoms, and each atom consists of a very small nucleus at the center, surrounded by a much larger, distant cloud of orbiting electrons. Every atomic nucleus contains some number of protons and neutrons. The number of protons in each nucleus determines the chemical element of that atom, or its Z number, while the number of neutrons in a nucleus, combined with the number of protons, determines the mass number of that atom, or its A number. This is because both protons and neutrons possess roughly equivalent masses, each about 1 atomic mass unit, or AMU. Additionally, all protons are positively charged particles, while all neutrons are charge neutral, so they offer no counterbalance to the collection of positively charged protons within the nucleus. So since like charges typically repel one another, what holds a nucleus together? This is accomplished by a fundamental force in nature known as the strong nuclear force, which attracts and holds protons and neutrons together within the nucleus using a measurable binding energy. Interestingly, the nuclear binding energy also reduces the total mass of each nucleus, which is known as the mass defect. This is an important point we will discuss later in this presentation. Returning to the atomic mass number, or A number, this is also known as the isotope number of an atom, and each element may exist in several isotopic forms. For example, all hydrogen atoms contain only one proton, so the Z number for all hydrogen atoms is 1. However, a total of 3 isotopes of hydrogen actually exist. Specifically, elemental hydrogen atoms, which contain no neutrons, so these nuclei have a Z and an A number of just 1. Atoms of H2, also known as deuterium, contain 1 proton and 1 neutron in their nuclei, so the Z number is 1 and the A number is 2 for these atoms. Likewise, atoms of H3, also known as tritium, all contain nuclei consisting of 1 proton and 2 neutrons, so their Z number is again 1, but their A number is 3. All 3 isotopes are forms of hydrogen. However, only the H1 and H2 isotopes are stable. The H3, or tritium isotope, is unstable, which means it undergoes radioactive decay. In fact, of the roughly 90 chemical elements found in nature, typically 2 to 3 isotopes of each element are stable, while the remaining isotopic configurations are unstable and result in decay. In the case of tritium, these atoms decay over time into helium-3 or He3 through a process known as beta decay. The beta decay process essentially converts a neutron within the nucleus into a proton while simultaneously emitting an electron or beta particle, hence the decay name. As such, this changes the atom's chemical element from hydrogen to helium due to the added proton. Other forms of radioactive decay are addressed in future videos within this series. So, we have a collection of positively charged protons and neutral neutrons within the nucleus. What are we missing? Balance. The necessary charge balance that enables atoms to collectively form into matter is provided by the electron cloud surrounding the atomic nucleus. Every electron carries an amount of negative charge equal and opposite to the positive charge of each proton. This is true despite the fact that every electron is around 2,000 times less massive than the much heavier protons and neutrons. So all charge-balanced atoms have an equal number of protons and electrons, and in the case of hydrogen, only 1 electron orbits the atom nucleus. The final particle type we need to discuss is the photon. To understand most nuclear weapon effects, it's useful to consider photons as individual, charge-neutral packets of energy that all travel at the speed of light, regardless of their energy. In the context of nuclear weapon effects, the photons of greatest interest are typically gamma rays and X-rays, which are classified as such based on how they are created. Specifically, gamma rays are emitted as atomic nuclei release energy, which most often occurs during atomic fission or certain types of radioactive decay. This means gamma rays tend to be born at high initial energies. In contrast, X-rays are born from either electron energy transitions within an atom's electron cloud or from free electrons as they slow down while traveling through matter. In both cases, X-rays are emitted from electrons, which tend to make them less energetic than gamma rays and, therefore, much less penetrating in matter and individually less dangerous to humans. However, X-rays are produced from nuclear weapons in significantly greater numbers than gamma rays, which is partly due to the sheer number of electrons present in nuclear weapon fuel relative to nuclei. This makes sense when you consider that each uranium atom has 92 electrons per nucleus, and each plutonium atom has 94. In fact, as future videos in this series will describe, roughly 70% of a nuclear weapon's yield is produced as X-rays. But where does all that nuclear energy come from? Well, to answer that question, we must again consider the strong nuclear force that holds protons and neutrons together within atomic nuclei. Remember, this force creates a binding energy across the nucleus that reduces the total mass of the nucleus, known as the mass defect. For heavy isotopes of nuclear weapons fuel, such as uranium-235 or plutonium-239, the total binding energy per nucleus is quite high due to the sheer number of neutrons and protons present, 235 and 239 respectively, per nucleus. So when these atoms fission into two or more smaller, more tightly bound nuclei, the excess mass is converted to energy in the form of emitted gamma rays and the kinetic energy of free neutrons and fission fragments. A similar energy release, albeit much smaller, is likewise produced during nuclear fusion, which is a process of creating a heavier atom from two or more lighter atoms, most often associated with isotopes of hydrogen. Usually, deuterium atoms are accelerated into either a deuterium or tritium target to create fusion events, each of which results in the production of a heavier helium atom and a free neutron imparted with high kinetic energy. This concludes this presentation. If you would like to continue learning more about nuclear weapons and their effects, please click on the link below. Thank you for your attention.